Hey, welcome back. Let's conclude our conversation on nuclear chemistry by talking about some actual real-world applications of nuclear chemistry. So there's two different types of nuclear reactions that we experience in our life. There are nuclear fission reactions and there are nuclear fusion reactions. We're going to talk about both. Understand that nuclear fission involves the splitting of a large atomic nuclei into fragments of approximately the same size. This occurs when a neutron is flying towards a larger particle, and then when that neutron collides with that particle, the particle shatters into other neutrons and other particles. This makes these other neutrons fly out and collide with other particles and do the same thing, and then those do that to this, and this does that to that, and it just kind of keeps going and going and going. It's almost like dominoes, and this is called a chain reaction. So an example of this, if we were to draw like kind of write out like an actual formula for it, let's say that I have uranium, so this is like 235. Let's say that I have uranium-235, and it is bombarded by a very fast, high-moving neutron. What it's going to do is it's going to break apart into two particles of similar mass. So I'm going to break apart into krypton, and I'm going to break apart into barium. And then I'm also going to produce 3 neutrons. And what those 3 neutrons are going to do is they are going to go and hit 3 more uranium molecules, or atoms, I should say, in this case, not molecules. But they're going to go off and hit 3 more uranium atoms. And then those 3 neutrons, so now we're going from 3 to 9, and then from 9 to 27, and no, right? So it just keeps going. So this also produces a bunch of energy when this happens. So that's why I'm writing energy really big. So it's a tremendous amount of energy is released in this process. So there is this point called critical mass. We need to have enough of a substance for critical mass to be reached. Once critical mass is reached, that's when a chain reaction occurs. If we have less than that, there's no chain reaction. So what happens if we don't have enough? Well, if we have too little of a substance, then there's no reaction. Nothing occurs. It just does not cause a chain reaction, and that's it. If we want to start a chain reaction for, say, for example, like uranium, not that this is something you would need to know, but we need about 40 kilograms of uranium to start a chain reaction, and then the reaction starts going. So where have we seen this? This is the science behind how they designed the atom bomb. The atom bomb, which is historically used in World War II. The atom bomb was powered by that particular isotope of uranium, uranium-235. So when the uranium bomb, inside the bomb, when it ignited, it was bombarded with neutrons, and those neutrons broke apart the uranium, which broke apart other things, and then the amount of energy released caused the atomic explosion. So this is one way that we have seen nuclear fission being used. Of course, we don't really use that kind of device anymore, but one that we see much more often and in our daily life is we see nuclear fission happening in nuclear power plants. So nuclear power plants consist of fission reactions that are maintained or controlled by what are called control rods. The control rods are the big factor here. With the atomic bomb that was dropped in World War II, or the atomic bombs that were dropped in World War II, there was no control. The chain reaction was allowed to react uncontrolled and cause havoc. But in a nuclear power plant, the control rods control the rate in which the neutrons are colliding with other substances by absorbing neutrons and like slowing down and speeding up the process depending on the input or output that the nuclear reactor wants to produce. We also have nuclear fuel, which is what powers most of these nuclear power plants. It's what we put in order to create energy in the nuclear power plant. Usually it's uranium-235, sometimes it's plutonium. And we also have things called moderators, and moderators are substances that slow down the speed of the neutrons, making it possible for them to, form fission or conduct fission. and they absorb the energy of fast neutrons, and it's usually something like graphite or water. So there's a diagram in your book that actually has a really good example of like how a nuclear reactor works. It looks like this. So notice inside the reactor here we have these rods. These are the control rods that are inside the reactor. So that's where the reaction is occurring, and the control rods are controlling the rate in which the neutrons are colliding with one another. And when they do this, they heat up and they provide steam, and the steam pumps, and then the water is also there as a moderator, but also it cools the whole system. So this whole thing is like submerged in water, and it's all very controlled. So if you've ever driven down the coast, maybe like towards San Diego or something, you might have seen on the shoreline there was these big domes. Those big domes used to be nuclear power plants that used to power the nearby military base, but they are not operational anymore. But we actually had a nuclear power plant pretty close to us. So there are a couple problems with this type of reactor. One major problem is the waste that they produce. When the uranium or the plutonium, when they're done, when they are spent and they can no longer conduct nuclear reactions, they just become nuclear waste. And they're really difficult to get rid of because, as you know, based on what we learned about half-life, things like uranium and plutonium have really long half-lives and they don't just go away. So we don't really have a really great solution for this. Right now our solutions are, like bury it deep, deep, deep underground or put it in like special fills. So maybe we'll figure it out later. Or unfortunately, sometimes nuclear waste ends up in the ocean, which is also bad. So that's kind of a drawback. Another drawback that a lot of people get nervous about is, say, for example, like human error. If you've heard about the disaster that happened in the Ukraine a long time ago in the city called Chernobyl, there was somebody, it was human error in the sense that people were supposed to be under control of the power plant. Things did not go as they should have, and the power plant overheated and exploded. And in that, the land around Chernobyl is still highly irradiated and difficult for anyone to be around. Recently, we had the issue in Japan where the tsunami sunk one of the nuclear plants, and then also again, that area got a little bit irradiated and a lot of that waste poured into the ocean. So these are some concerns for these plants, and here in the United States, we're actually a bit unique in that we don't have a lot of nuclear plants. We still use a lot of fossil fuels or coal in our powering, but a lot of places, say for example in Europe, they actually have primarily nuclear power. And although we use a lot of coal and fossil fuels here in the United States, I would not be surprised, or you should not be surprised perhaps in your lifetime, if you start seeing more and more nuclear plants pop up, mostly just because uranium is something that is pretty abundant and it can be made, whereas fossil fuels and coal and things like that are things that we're only simply using, and there is a finite amount. And it is difficult for us to make more of it because it took so many millions of years for it to be made in the first place. Whereas uranium is not so much the case. I mean, you can take uranium, you find it's pretty abundant, you just have to prepare it, and then you can do your thing with it. And it produces a lot of energy, as we learned previously. A nuclear reaction is 10 times fold more energy abundant than, say, a reaction with something like coal. But again, that's something to keep in mind. So that's fission. Let's talk about fusion, which is the other type. Fusion is kind of like the opposite. Instead of things breaking apart, it's about things going together. So two or more light atomic nuclei combine to form a single, I don't know why it says single, to form a single nucleus of slightly less mass. So in this situation, this is actually something that we experience daily because it's the reason why we have a sun. So all stars in the universe conduct nuclear fusion. And the example of this is, let's say that we have two particles. These are called deuterium particles. So we have two H particles, and they combine together to form a helium particle and lots of energy. So this is a big energy reaction. This happens in our sun. So our sun is composed of mostly hydrogen, just fusing together to form helium and then kind of repeating and doing this in like one giant reactor. And this is also how a hydrogen bomb works. This is another type of a highly destructive device. We Fortunately, have not used any of this in any sort of conflict, but the hydrogen bomb does exist. It's much, much, much more powerful than the atomic bomb. And it's, again, fortunately hasn't been used yet, but we'll talk a little bit more about it in a second. So you might think to yourself, well, why don't we just use fusion reactors then? This sounds like a good deal. I mean, there's no waste, right? We're not producing nuclear byproducts. And there's plenty of hydrogen in the universe. In fact, hydrogen is one of the most abundant elements in the universe. So this sounds like a no-brainer. Like, why don't we just have nuclear fusion reactors all over the place? And we're good, right? Little suns all over the place. But the problem is that it takes an incredibly high amount of energy to kick off the fusion reaction. And in fact, there are some theories that state that we wouldn't really be able to have any sort of container right now in our current state in science to contain the energy that would actually be released from a nuclear fusion reaction. We don't have anything to sustain it. There are some researches or theories going on about how maybe we can disperse that energy across magnetic fields or things like that, but it gets a little in the weeds. But it's hard to harness the power of the sun when we're here on the Earth, and that can be dangerous. So that is one thing that we struggle with. But again, the equation that it has here, this is just the same equation that we were talking about before. This is also an equation, this is like kind of an alternate version of it. I think this is the one that's in your book, where we have a deuterium and a tritium, which is what the hydrogen with the 3 is. They react together to perform helium and 1 neutron. And again, tons and tons of energy. But just to kind of talk a little bit about that activation energy, like to kind of go back to the hydrogen bomb. The hydrogen bomb, in order to make the hydrogen bomb actually go, it needs to have a nuclear fission reaction to cause it. That's how high the activation energy is. So just kind of imagine that. It requires the energy of a nuclear bomb to power this other bomb. So you can see that the activation energy, the little spark required to light this, is the power behind a nuclear weapon. So it's a pretty seriously high activation energy. And unfortunately, that's the limitations that we have. Perhaps one day, in some sort of future science, we will be able to harness nuclear fusion in a really effective way. But as of right now, it's still something that seems to be a little bit out of our reach. So those are the two types of energy and reactions that we use with nuclear chemistry. And that's it. That's it for nuclear chemistry. We'll see you next time.